Now, I mentioned in the textbook that this interaction hypothesis tested statistically through the GLM procedure is dependent on sample size. So you also want to consider evaluating the hypothesis from an effect size perspective. And I mentioned simulation research in the textbook that has shown that as long as the association difference is less than 0.40 across your groups, then you probably have satisfied the assumption sufficiently in order to carry out a regular ANCOVA. Now, how to do that? Go into Data, Split File, Compare Groups, and put sex into this grouping variable. So I'm going to get regression weights for males and females separately. Click OK. Click Analyze, Regression, Linear, and I want brain size kilograms as the dependent variable and body size factor as the independent variable. In the context of the ANCOVA, this is the control variable and that's the dependent variable. But in the context of evaluating this analysis, it's an independent variable with respect to the assumption of homogeneity of regression slopes. Click OK, and SPSS has produced two portions of the output for the coefficients table. We've got females where the standardized beta weight between body size factor and brain size is 0.288 for females, and it's 0.124 for males. It's both positive, so a larger body size is associated with a larger brain, and they are comparable between males and females. They're not exactly the same. So let's calculate that. 0.288 minus 0.124, and that equals 0.164. And that is a lot less than the maximum 0.40 difference that the simulation research suggests is acceptable. So I can feel confident, in addition to the interaction hypothesis I tested, which is sample size dependent, I can feel confident with this effect size approach to suggest that the ANCOVA can probably be used because the assumption of homogeneity of regression slopes is probably satisfied. Now, the last thing I did in the chapter with respect to this assumption is that I created a scatter plot to look at the association visually, separately across the sexes. And one way to do that is to create a scatter plot and then separate across the groups. Before I can do that, I got to click on Data and unsplit my file. Now I can go into Graphs, Chart Builder, and click on Scatter and double click on Group Scatter. Now I've got the sex variable here, and importantly, I've specified in the data file that it is a nominal scale. This utility in SPSS won't recognize it as a grouping variable unless it's nominal. So I'm going to set the color as sex. That means it's going to separate across males and females in the scatter plot. Now I also need brain size kilograms as the dependent variable on the y-axis and body size factor on the x-axis, because that is the covariate. Now the last thing I need to click is subgroups. I want SPSS to create a line of best fit for both males and females separately, and click OK. And here is the scatter plot produced, version 25. The scatter plot is similar in look to the one that I produced in the textbook, but it's also a little bit different because it's a different version of SPSS, and I just manipulated it a bit different. You'd have to click on a few things here to make it look pretty. So I'm going to hide that there and delete that, and probably delete this thing here. And there's more work that could be done to make this chart look good, but this is how I did it. You can make it a bit smaller, change the font sizes, and make things bold. We can see that females have a steeper slope, which is consistent with the larger standardized beta weight for females in comparison to the males. It even crisscrosses here at a point, and I mentioned in the textbook that that's a little bit of a concern. But if we count on the simulation research, which says that a maximum of 0.4 is allowable, and we've even looked at it from a statistical significance perspective, and it's been satisfied, overall I feel like the assumption of homogeneity regression slopes has been satisfied in this case.